Okay, we're going to go ahead and start part two, which is going to be on atomic radii. I think I'm just gonna change the color of the pointer. All right, so atomic radii is the plural form for atomic radius, and it's just a way to measure how big an atom is. You can define it. I think it's quite self-explanatory. It is the distance between the nucleus and the valence electrons, or you can say the nucleus and the valence shell. It's probably a little bit hard to capture an electron, or if you have multiple electrons, it's the shell. And you can also define it as one half the distance between the nuclei of two atoms of the same element, which is another way to do it. But either way, you get the distance between the nucleus and the valence shell. It is usually expressed in picometer. It's just a very, very small amount. So 1 picometer, which is pm, is around a trillion or 10 to the power -9 of a meter. We're going to talk about conversion of unit a little bit more in the future, but right now that's the only thing I'm going to say regarding atomic radius. Okay, and I think it's hopefully this is something that's not hard to understand. The more the valence electrons are attracted towards the nucleus, so let's say if I have a nucleus in here and then I have some shells. Now, and I'm rather impressed with my drawing of circles and whatnot. So if we have this, maybe we shouldn't put it there. Okay, that's marginally better. What just happened? This is obviously highly entertaining for the people who are watching this video of me drawing and failing at drawing multiple. Um, I don't know where I'm going with this actually. Let's try that. Okay, so if you compare these two atoms, which I'm trying to indicate, let's say they both have a core charge of 1, but this one has another shell compared to this one. So this one, because it has one less shell, so let's assume this is lithium and this is sodium, it is going to, that's not sodium, I don't know what that is, that's hydrogen and that's lithium. Okay, this one has less shell and more attraction, therefore you would have more attraction between the nucleus and the valence electron, between nucleus and valence electrons. And if the nucleus is more attracted to the valence electrons, it's going to pull the valence electrons closer towards it. So if it pulls the electron closer towards it, that is going to decrease radius. Decrease radius. Okay, I think that's fairly straightforward to understand, hopefully. Let's go back to black, but that's just way too severe for my liking. I have no idea where I'm going with that, so that did not work out too well. Anyway, moving on to the next slide. Predict and explain the trends in atomic radii down a group and across a period from left to right. So I think there was a little bit of a misunderstanding of this question in class. The question is not asking you to incorporate both the direction down a group and the direction across a period. This is actually two separate questions. You're going to describe the trend down a group, predict and explain the trend down a group, and then predict and explain the trend across a period from left to right. Okay, so once again, if you really want to attempt this question, you can pause the video and actually do it. I'm not gonna wait 5 minutes. Now, if we start with the left to right across a period, you're going from left to right. Again, this part doesn't change. You're going to have an increase in the number of valence electrons while the number of occupied shells remain the same. And core charge increases as a result of an increasing in number of valence electrons, which increases the attraction between the nucleus and the valence electrons. And that effectively would decrease atomic radius, or the nucleus is going to pull the valence electrons closer towards it. So even though the elements have the same number of shells, the shells actually get smaller. So we compare lithium, which has 3 protons, and Okay, so we have 2 here, and let's say we have another one here. This is lithium. If you get to fluorine, which now has 9 proton, it's going to have smaller circles. I feel like I kind of shoot myself in the foot because I now have to try to make this smaller, and I'm not sure how I'm going to do that. So even though it has more electrons, the circle actually should get smaller. And obviously, this is another representation of an atom. I don't think they actually look like circles, but compared to lithium, fluorine is going to be smaller, even though it has more protons, more electrons, and actually is heavier in terms of, the mass. Anyway, so if we talk about this answer going cross period, this is just a repetition of what I just said. Make sure you talk about the attraction between the valence electrons and the nucleus before you link it to atomic radius. Similarly, when you talk about going Dow group, I think that's actually very easy to understand. You have the same core charge, but you increase the number of occupied shells and also decrease the attraction between valence electrons and the nucleus. So that will push the valence electrons away from the nucleus and increase atomic radius going down a group. Okay, so if you increase if you increase the attraction between valence electrons and the nucleus, you will decrease atomic radius. And the opposite also holds true. If the attraction between the valence electrons and the nucleus decreases, atomic radii will increase. Okay, this is one form of representation of the atomic radius. I don't think I gave people this diagram, although if you really like it, you can print it out. But it does show how the atoms get bigger going down and get smaller going across. Now, I do want to annotate this diagram a little bit. I think I started doing it, but this is a way of plotting the actual atomic radii with increasing atomic number, and hopefully you can see the different trends. So if we just change, let's go with red. So from lithium to neon, this is going across a period. From sodium to argon is another period. And from potassium to krypton, that's also a period. So this is going across a period. And you can clearly see a general trend of decreasing in the atomic radius as you go across a period. There are some fluctuations here because once you get to potassium, this is the transition metal, and they don't always follow our prediction. I'm not going to talk about that at this point. Okay, fluctuation. And did I even spell that right? Anyhow, if you go down a group, you can actually see the relationship between the element down a group if you just look like this. So even though it is going down a group, there is an increase in atomic number, obviously. So if I go in this direction, this is down a group, and there is definitely an increase in atomic radii going down a group. Let's say this is group 1. So if I go from lithium to sodium to potassium to rubidium, there is definitely an increase in atomic radius. Similarly, you can see an increase. Okay, I shouldn't have done that. You can see an increase as I go down group 18 or the noble gases. In that, all right, maybe we shouldn't do that at all. Let's just circle. So we go argon, krypton, neon, and helium. This is group 18, the noble gases. You also can see an increase in atomic radius. Okay, so that's that. Now this also allows you to compare the sizes of specific atoms, so we can pick any 2 atoms. I think the trick with these questions, when you need to make a comparison, is to actually look at their positions on the periodic table. So we look at part A. Once again, if you really want to try to do this question yourself, this is the point to pause the video and you can continue watching once you're finished. But the point here is to look at their positions on the periodic table. So magnesium and calcium actually belongs to the same group, group 2, and oxygen and fluorine belongs to the same period, I believe. Okay, so when we look at part A, magnesium and calcium belong to the same group, which means that they have the same core charge. So any difference is going to be due to the number of occupied shells. Even though they have the same core charge, magnesium has 3 occupied shells, while calcium has 4, which means the distance between the valence electrons and the nucleus would be larger in a calcium atom compared to a magnesium atom. So calcium atom will have a larger radius. I do think it's a good idea to get into the habit of making comparative statements when you need to answer questions that ask for comparison. So I'll be looking for things like a calcium atom has more occupied shells than a magnesium atom. It's not enough just say it has more shells or it has shells, because that actually doesn't do a comparison at all. You have to make a comparison because the question asks for it. And so I want to see things like has more, this is larger, the radius, something like that. So be very, very specific with your comparative statements. Make sure you have the two things that you're trying to compare clearly stated in your sentences. Similarly, when we have part B, I will start by saying that they belong to the same period, and then my comparison would spring from the properties of elements in the same period. In this case, they have the same number of occupied shells, but one has a lower core charge than the other. You can also say that one has less valence electrons or less protons, but core charge is a nice way to sum all of that up. And so the valence electrons of oxygen is not as attractive. This is another comparison. We're talking about the attractiveness between the nucleus and the valence electrons in an oxygen atom compared to a fluorine atom. And because the valence electrons of oxygen is not as attractive to the nucleus as the valence electrons of fluorine, oxygen atom will be larger. So try to make sure that you have comparative statements when the question asks for a comparison. And lastly, we have part C, nitrogen and aluminium. Now this is when you have a change in both the core charge and the number of electron shells, but it's actually not that difficult to make a comparison, because nitrogen is I wouldn't say, well, it's not a double negative or anything like that. It's just comparing both core charge and number of electron shells. It's fairly easy to see why nitrogen is going to be smaller, or I guess I haven't actually answered the question here. I have to say that aluminium is larger than nitrogen. Okay, so first of all, nitrogen has a higher core charge, which means that you can, and then it also has electron shells. If you really want to extend this answer, I guess you can say that because of this, the valence electrons would be more attracted to the nucleus in a nitrogen atom. More attracted to the nucleus in a nitrogen atom. So I guess that's one way to extend this answer. But ultimately, you can deduce that aluminium is going to be larger than nitrogen. Another way to answer this question between nitrogen and aluminium, and I guess you could do this if you have a multiple choice question and want to really quickly answer. The question is, if you look at the periodic table, and I'm just going to recall what we had before, so we go across a period from left to right, there is an increase in the attraction between the valence electrons and the nucleus, so the atomic radius actually decrease, so decrease in atomic radius. And if you go down, because the attraction between the nucleus and the valence electrons decrease, there is an increase in atomic radius. Okay. So if you have something like that, I could pick, say, for example, phosphorus, because atomic radius increase as you go down, then I know from here that nitrogen is going to be smaller than phosphorus, and because atomic radius decrease going from left to right, I know that phosphorus in turn is going to be smaller than aluminium. Hence, you can make a conclusion that nitrogen, why did I say sodium, must be smaller than aluminium, or aluminium must be the larger element. So that's another way to compare elements that do not belong to the same period or group, you can pick an intermediate and compare them. But I think it's perfectly possible to just look at both the number of shells and the core charge and make a direct comparison. So this is just a setup of that if you really want to. That is the end of electronegativity.